move ahead, we will be judging the details of these particulate matter in depth, because this is a question which is very important from examiner point of view. So you can see in the picture, and this derivation have been nicely given in the book of Gilbert M. Masters or any good environmental chemistry book. So let us suppose we have a spherical aerosol particle, and aerosol are nothing, these are the solid or liquid particles suspended into air with a negligible terminal velocity or fall speed. So you can have a look in the picture which is given there in this, that particulate material which is almost spherical nature suspended into air having a diameter d and density rho of the material. When it is freely floating into that air, it is having a weight which is acting downward, which is mg, and if it's freely floating with a negligible velocity into that air media, then it will be having a viscous drag, which is nothing but the viscous drag force, which is 6 pi eta, where eta is the coefficient of viscosity, r, which is the radius of the sphere, vs or v, which is the settling velocity of the aerosol particle into the air. So we will be, if it is an equilibrium, then we will be equating both these force, mg equal to 6 pi eta r vs. And now we can write down this r term in terms of diameter. So the r will be replaced by d by 2 on the right hand side. Now all of us know the density is mass by volume. So mass here on the left hand side can be replaced by density into volume. So we replace the mass with density into volume. And volume of the sphere, all of you know, is 4 by 3 pi r cube. Or if I replace r in that volume with d, so it will be 4 by 3 pi d by 2 whole cube. And if we will solve it, then it comes out to be 1 by 6 pi d cube into g. So we got the volume as 1 by 6 pi d cube into g. So we will be replacing this term of the volume. Then we will be having on the left hand side, that is 1 by 6 pi d cube into g rho, and subsequently cancelling out everything, we got, and replacing each and every term of radius with the diameter, we got 1 by 6 pi d cube g rho equal to 3 pi eta d vs. And subsequently solving this equation for vs, which is settling velocity or terminal velocity of the aerosol particle, it comes out to be that vs is equal to rho, which is density of material, g acceleration due to gravity, d square, which is the diameter of the aerosol particle, upon 18 eta. So vs is equal to rho gd square upon 18 eta meter per second, where vs is the settling velocity in meter per second, rho is the density of material, eta is the coefficient of viscosity of air, and here the coefficient of viscosity for air is 0.172 gram per meter second. So from this equation we can see that settling velocity is directly proportional to the diameter square, directly proportional to the density, also directly proportional to the acceleration due to gravity, and inversely proportional to the coefficient of viscosity. Further, analyzing this equation of settling velocity, we can say that more the settling velocity, more will be the diameter. Means more the diameter, more is the settling velocity, because settling velocity is directly proportional to the diameter square. And here we can analyze the settling of larger and smaller particle. And you know velocity is distance upon time, means velocity is also inversely proportional to time. So we can see it like this. Let us suppose we have a larger particle having more diameter, having more settling velocity, so it will take lesser time to settle. So that's why the larger particles settle faster. Assume a small particle which is having a small diameter. Then settling velocity will be small. Hence, it will take more time to settle. So that's why we generally say that large particles take lesser time to settle down, because they are having high settling velocity and take less time. On the other hand, smaller particle having low diameter, having lesser settling velocity will take more time to settle. That's why the small particles are more dangerous to health, because they settle late. Now coming to the details of particulate matter. We will be dealing about the details of these particulate matter one by one, so that your understanding become better about it. So particulates or particulate matters. These are small size particles which are much more dangerous than the large size particles, because larger the size particles, when inhaled, gets filtered from the nasal tract, which is our first line of defense after skin. It is a smaller particle which escape the natural filtering and settle deep into lungs. Particles of size less than 10 micrometer can be termed as RPM or respirable particulate matter. Particles can be classified into different types according to the size and physical characteristics. So these are the different classification of the particulate matters, which is very nicely explained into the book of Gilbert also. You can read it for reference after the notes. First is aerosol. So aerosol, as mentioned here, these are the colloidal solutions in which the dispersion medium is air and dispersed phase is either a solid or a liquid, or simply we can define as aerosols are solid or liquid particle less than 1 micrometer in size suspended into air having a negligible fall speed or terminal velocity. Then we talk about fumes. These are solid particles having a size less than 1 micrometer. Coming on to soot or black carbon, which is solar radiation absorbing anthropogenic pollutant. So it is very finely divided carbon particles clustered together in long chain formed due to incomplete combustion. For example, the particle which are emitted by the combustion of dhoop. Now coming to the mist or fog, these are liquid particles up to a size of 100 micrometer, and generally you remember this also when you talk about aerosol. These are colloidal particles having size 1 to 1000 nanometers. This is a very famous repetitive question. Coming to the dust. So dust is nothing but solid particulate matter formed by crushing or grinding operations. So dust is nothing, it is a solid particulate matter formed by crushing or grinding operations. Now we will be talking something about aerodynamic diameter, which is very important when we talk about aerosols. It's very, very important whenever we talk about aerosols. So aerodynamic diameter, if we assume, is like that. If we have a perfect sphere of substances like polystyrene and we compare it with the particle which we are studying, suppose aerosol particles. So aerodynamic diameter is defined as the diameter of a particle having the same settling velocity and same density as that of particle under considerations. Means for defining aerodynamic diameter, we have to assume a perfect spherical material to define the aerodynamic diameter of a particle which we are studying. So we will not be going into the details of definition of aerodynamic diameter. Although the particles may have irregular shape, their size can be determined by an equivalent aerodynamic diameter, determined by comparing them with the perfect sphere having the same settling velocity and same density. So which is nicely defined here. The particle of most interest having an aerodynamic diameter between 0.1 and 10 micrometers. So the most interesting particles are the particles who are having aerodynamic diameter between 0.1 and 10 micrometer. because particles smaller than 0.1 micrometer can undergo a random Brownian motion, while larger particles of size more than 10 micrometer settle so quickly. The particles which make it into lungs may or may not deposit there. Some particles are so small that they tend to follow the air stream into the lungs and then come out again. So they will be coming out after you breathe in and out. They are such a small particles. Roughly, particles with a size range of 0.5 to 10 micrometer are small enough to reach into the lungs and large enough to be deposited there by sedimentation. However, they ask this question, that the sedimentation of aerosol particle is more effective in the range of 2 to 4 micrometers. So, however, the sedimentation is more effective in the range of 2 to 4 micrometer. Now we will be classifying these particulate matters on the basis of their aerodynamic diameter, on the diameter of the aerosol particles. So there are two types of particulate matter, PM10 and PM2.5. So when we define PM2.5, so this 2.5 represent the diameter in micrometer. So the particle of size less than or equal to 2.5 micrometer in diameter is called as PM2.5 or fine fraction of a aerosol. Now we will be having a PM10 or a range of PM2.5 till 10 micrometer. This is called as coarse fraction of the PM10. So you can see here that PM10 can be divided into two categories. One is PM2.5, which is called as fine fraction of the PM10. Another one is ranging from a diameter less than 10 micrometer and more than 2.5 micrometers. So the diameter will be from the range of greater than 2.5 but less than 10 micrometer. This is called as coarse fraction of PM10. So we can easily understand this, that PM2.5 where the aerodynamic diameter is less than equal to 2.5 micrometer, and PM10 is when the aerodynamic diameter is less than 10 micrometer in range. And for details you can refer Gilbert Master regarding this topic. It has been nicely explained in the Gilbert Master book. Again, CO carbon monoxide, this is a colorless, odorless, tasteless, poisonous gas. And this was the lecture presented by A.S.S Science Foundation, Delhi. This was all about primary pollutant. In the next section, we will be starting the secondary pollutant. Hope you enjoy today's lecture. Thank you.